So we are venturing into learning about the sine curve. So today I'm going to teach you about the parts of the sine curve, and then we're going to talk about two aspects of transformations of the sine curve. So the first idea is let's learn about the parts of the sine curve. First, we have to realize that the sine curve is generated by revolving around a unit circle. Okay? So I've only drawn a piece of the sine curve. I haven't drawn the entire sine curve because after all, if we looked at the entire sine curve, we'd be looking at a huge distance from negative infinity all the way to positive infinity. So we're going to just look at pieces of it. The way that we're going to draw and sketch a sine curve in this class is we're going to use 5 easy to remember points that represent the sine curve. Okay? And those points are here. Okay? At 0, 0, I have a point that's on the sine curve at 0, 0. Okay? Now I'm going to end over here at 2 pi. So I've gone from 0 to 2 pi. Why am I only going from 0 to 2 pi?
That's a full circle.
Because that's one full circle, right? And indeed, that is the period. The period of one full cycle of a sine curve is equal to 2 pi. And that's 2 pi radians to be more precise, all right? So so far I have 2 points. I have 0, 0, and I have 2 pi comma 0. What about that point that's in the middle? What point would this have to be? This would have to be pi. Very good. So pi comma 0 as well. So notice that there are 3 points when we sketch a sine curve that are all on the midline. And what I mean by the midline is this point right here, this line, right? That's the middle of the curve, meaning it's half of the curve is below that line, half the curve is above that line, right? So the other 2 points that we're going to use are right here. What point would be halfway between 0 and pi? Pi over 2. And at pi over 2, what's the output value? 1. Very good. The output value is 1. And then the fifth point rather, would be this point here. And what point would that be? 3 pi over 2. Yeah, exactly. 3 pi over 2. And the output value would be negative 1. So here are the 5 points that we're going to use every single time that we're going to graph a sine curve. They are 0, 0, pi over 2, comma 1, pi, comma 0, 3 pi over 2, comma negative 1, and 2 pi, comma 0. Okay, those are the 5 points. You don't need to label them every single time, but I want to at least point them out to you. Do you notice that those points are the same values that are on the unit circle? So if you look at your unit circle and I ask you what's the sine of pi over 2, then you'd be looking at the y-coordinate for the value of pi over 2, and that y-coordinate would have a value of 1. Does that make sense? So this curve is nothing more than the collection of all points that are on that unit circle between 0 and 2 pi from what I can see here, right? And these 5 are the really easy ones to identify. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and then 2 pi 0. Are we okay so far? All right. Let's open this conversation up a little bit more then. What would the domain of my sine curve be? All reals. Absolutely, it's all reals. Remember, we're plugging in radians to the sine curve, right? I'm asking like the sine of pi over 2 radians, the sine of pi radians, the sine of 5 radians. So the input are angles. Well, I could take the sine of any angle that I want, right? I could do the sine of negative 3 pi over 2, positive 3 pi over 2, sine of 50 pi over 2. It doesn't matter, right? This curve goes on and on and on in both directions. So the domain is all real numbers. However, what is the range of the sine curve? Very good. Absolutely. The range is stuck between negative 1 and 1. And we include those points. They are part of the range. So we can use a bracket to include those points, all right? So far, so good. What about the amplitude? The amplitude is the distance from the midline to the highest point, or the amplitude is the distance to the lowest point. In either case, it's a value that is positive. So in this case, the amplitude, very good. The amplitude is equal to 1. It's the distance from the midline to the high point or the low point. It's always considered a distance, and it's always positive. How are we doing so far? Pretty good? All right. This is enough to introduce the parts of the sine curve. So if you look at the half-colored salmon sheet of paper that I gave you yesterday, it's kind of like a little guide to how to graph sine functions. So there are 4 different types of transformations that we could have or perform on a sine function. They're located at the bottom for you. Name one of them. Yeah, a vertical transformation, okay? A vertical transformation. That's just a fancy word for up or down, right? We can move sine curves up or down, the whole physical curve, up or down. What's another transformation we could do? Amplitude, nicely done, amplitude. And amplitude is the distance from the center line to the top or the bottom, right? So we just talked about that one. What's another one that we could do?
Period.
Yes, period, very good. And what's the period defined as? Yeah, the time that it takes to complete one full cycle. And what is that number of radians? 2 pi, beautiful. And what's the fourth one that we can do? Phase shift, very good, a phase shift, all right? And for today's lesson, we're only gonna focus on these 2 of the 4. So this is what we're gonna focus on today. I'm gonna show you how to graph sine curves with a different amplitude and a different period other than just the normal one, okay? That's where our focus is going to be. Okay, example A for how to graph curves with amplitude. We're going to do this one, y equals 4 sine of x. The first thing that I want you to realize is that the 4 is being multiplied by our sine function. Or rather, our sine function is being multiplied by 4. Notice where the 4 is. It's the number right in front of the trig function. Could be sine, could be cosine, could be tangent, but any number that's multiplied in front is going to affect amplitude, okay? So it's important that you can just look at the graph, or excuse me, you could look at the equation and you know ahead of time what the number is going to do to the graph, okay? So in this case, that number 4 is going to increase the amplitude, all right? So how do we sketch it out and draw it? Here is what we do, okay? First, give yourself a good-sized coordinate plane, and we're going to go from 0 to 2 pi. Because after all, the period has not changed. We're going from 0 to 2 pi. What has changed, though? The amplitude. So instead of just going to 1, like we normally would, 1 and negative 1, I have to increase the amplitude to what number?
4.
To 4. So I have to go all the way up to 4 and all the way down to negative 4. Okay? So notice we use amplitude to scale the y-axis. Does that make sense? Amplitude is what scales the y-axis for us. Okay. Great. Awesome. So let's label our x-axis. Our x-axis in between 0 and 2 pi is pi. So notice that it doesn't really matter where I put the pi, as long as it's between 0 and 2 pi, like halfway, in terms of like on the graph paper. That part doesn't matter, as long as it's halfway between 0 and 2 pi. What's halfway between 0 and pi? Pi over 2. So always think in terms of halves, right? So that means that the point between pi and 2 pi has to be 3 pi over 2. And if you don't know that, you just count by pi over 2s. 1 pi over 2, 2 pi over 2, 3 pi over 2. There you go. Okay, so here's what we do. The first one that we're always going to graph is we're going to graph the parent function sine of x. We always graph that one. Yes, we always graph that one. 5 points. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi. And I usually make this one like a dashed line to kind of give myself just like a representation of, okay, that's where we start. That's where we start. Then I usually pick a different color and I graph what I'm trying to do. Y equals 4 sine of x. Well, I know the 4 is going to increase the amplitude. So what happens to the point 0, 0? Where does it go? It stays at 0, 0. Why does it stay at 0, 0? Very good. Because the output of 0 is multiplied by 4, which is 0. Where does the point pi over 2, 1 go? Pi over 2, comma 4. So I'm going to label this one pi over 2, comma 4. So pi would stay there. 3 pi over 2 goes down to -4, and 2 pi comes back. So when I'm all said and done, I'm looking at this graph right here. The highlighter is for your final graph. So you take a highlighter and you highlight your final graph. All right, this is what we're going to use Desmos for. We're going to actually check to make sure that what we have done is actually correct. So you can go to just go to desmos.com. Doesn't have to be the one that I gave you yesterday. And you can see here that I've inputted the graph y equals sine of x, and I've changed it to that dotted graph line that we're using in our class. So this is kind of the ghost curve. This is kind of what we're using. And notice that if I zoom way out, right, we can see that the domain of this thing is indeed all real numbers, right? It goes on and on and on forever and ever and ever. But we're not concerned with that right now. We're concerned with this new function that we graphed, which was y is equal to 4 sine of x. All right? And you can see that the difference between the dotted one and the purple one kind of looks like ours. But just to make sure and check, we're going to plug in the point that we have chosen to check. And what point did we choose? We chose this one, pi over 2, 4. So if we go back and we plug in, and you can actually bring up the keypad in Desmos and say pi divided by 2. And then you can actually put a comma in and put the number 4. And look, it shows up exactly on the graph, and you can actually click on it to make sure that that point lines up perfectly with the point that we came up with right here. So we are using this nice visual program to check to make sure that what we have done here, pi over 2, 4, matches with what it actually is. All right, y equals -2/3 sine of x, another amplitude example. What's different about this one? Yeah, what does that negative mean? Exactly. So this is going to be an amplitude with a reflection. Okay, amplitude with reflection. We can do that move in one fell swoop. So I'm going to make this a little smaller. I'm going to give myself a nice coordinate plane. Okay? I'm going to go from 0 to 2 pi because my period has not changed. Halfway between is pi. Quarter of the way is pi over 2. 3/4 of the way is 3 pi over 2. All right, if this is a value of 1, then this is my value of -1. So that's like 1/3, and that's like 2/3. That's like -1/3, and that's like -2/3. Okay, so far so good. We always graph the ghost function first, or the parent function. So I've got 0, 0, pi over 2, 1. Pi 0, 3 pi over 2, -1, and then 2 pi. So notice it's the same 5 points over and over and over again, okay? So there's kind of a sketch of my ghost function, okay? Then the next idea is, or the next one that we're going to graph is y equals -2/3 sine of x. Okay, the negative means I reflect. 2/3 means that I have decreased the amplitude from 1 to 2/3. So where's the point 0, 0 going to go? It's going to stay there. Very good. Where's the point pi over 2, 1 going to go? Pi over 2, -2/3. I have flipped it over and gone 2/3 of the distance. How about pi 0? Stays there. How about 3 pi over 2, -1? Very good. And then 2 pi 0, of course, stays there. So that's what we've got. Okay. The highlighter is for your final graph. So we're going to highlight the final graph. Okay, what point should we check? What would be a good one to check? Let's do this one. Let's do 3 pi over 2 and 2/3. Why do I not just pick 2 pi 0? Or how about pi 0? How come I'm not picking that one for this specific problem? Because it didn't change, right? They didn't change. How do I know? That hasn't changed much, right? Okay, let's go over Desmos. Here we go. We want to graph -2/3. So you can actually just punch in -2/3 sine of x, right? Oh, look, this point is no longer one of them. That's way out of there, so we're going to get rid of that one. So the point that we're going to test is 3 pi over 2, and we said then -2/3, right? That's not right.
Did we say positive 2?
Oh, I said positive 2/3. Thank you. Thank you. Whew. See how I checked? I knew it wasn't right because it wasn't in the right spot. All right. That's actually a good thing to have happen. So check it out. I have now see that the point 3 pi over 2 2/3 is indeed on the graph of negative 2/3 sine of x. So that means it matches what we have done on our sketch. So everything looks pretty good. Okay, here we go. Let's move on to period now. This is the second idea for the day. Examples of period. First of all, you should notice that the way that this function looks is very different than the last example, right? I gave you the same numbers more or less, but notice where the numbers are. I have 2x over 3. Look at that salmon colored paper and find where the period is located. How do I determine what the period is? It's after the sign, but before what? The variable, the x, okay? So how could I rewrite this so that I could have a number between the sign and the variable? Yes, Mia?
You could do sine and then 2/3.
Very good. This is the sign of 2/3 x. Do you see the difference? Do you see where the 2/3 is? It matters where it is in the equation, okay? This is the sign of 2/3 x, or 2x over 3. This is not 2/3 times the sign of x. It's different. This number has an effect on the period, okay? So that's the first thing that we have to understand, is that if my number is between my sine function and my variable, it's going to affect the period, not the amplitude. Okay, so now I know it's the period. How do I get the period? How do I get it? Yeah. Look on that pink sheet. It'll tell you.
2 pi divided by
Exactly. We take 2 pi and we divide it by the number that we are using in our equation. Okay? The reason being is because the 2/3 stands for we've only completed 2/3 of a full cycle on a period of 2 pi. So therefore, when we do this little calculation, 2 pi divided by 2/3 is 3 pi. So the period of this particular function is 3 pi. That means it has to complete one full cycle of those 5 dots in a distance of 3 pi radians. So the most what am I trying to say? Oh, the most common error, that's it. The most common error that students make on this type of problem is I'll ask them, hey, look at that equation and tell me what the period is. And what do you think they all tell me? 2/3. Okay? 2/3 is not what the period is. Yeah, the period itself is 3 pi. 2/3 means that you've only completed 2/3 of the actual period on a distance of 2 pi. That's what that means. I'll show it to you visually, okay? So anyways, let's go on. How do I graph this now? All right. Well, I have to set my scale up a little differently. So notice that if we used amplitude to scale the y-axis, we're going to use period to scale the x-axis. So here we go. I need to start at 0 and I need to end where? At 3 pi. I need to end way over here at 3 pi. So that's going to be what one period is worth, okay? So then that means that if I call that pi, then I'll call this 2 pi, and my scale is all good so far, right? Okay. And then the amplitude I know is going to be 1. That part is unchanged, so there's -1 down there. So I've got 1 and -1. So the first thing that I'm going to do is I'm going to graph y is equal to sine of x. That's my parent function. I'm going to graph that on the coordinate plane here. Okay, so this is going to be pi over 2, and this has to be 3 pi over 2. And I need these points to help me graph the sine curve. So I'm going to have 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and then finally 2 pi. So here is my ghost curve. Okay? Okay, there's my 5 dots. So now how do I work with these 5 dots to actually make a sketch by hand of y equals sine 2/3 pi? Well, here's how we do it. I'm going to pick a different color, and I'm going to graph for you y is equal to the sine of 2/3 of x. Okay, where's my starting point going to be, you guys? 0, 0. It's going to start here. Okay? Start there. Where is it going to end? It's going to end at 3 pi because that's my new period, right? I need to start and end on a distance of 3 pi. That's my period. Great. Well, what's the halfway point between 0 and 3 pi? 3 pi over 2. So I know halfway I am going to be at the midline again because that's how the sine curve operates. Remember, it goes midline high, midline low, and then back to the midline again. So I have 3 of my 5 dots plotted on my graph. I just need some more dots, don't I? Yeah, I need this point. What's halfway between 0 and 3 pi over 2? 3 pi over 4. So this point has to be 3 pi over 4. Now, if you don't see that, just divide pi over 2 by half. Look, this is 1 pi over 4. Then I have 2 pi over 4, then 3 pi over 4. Pi would be 4 pi over 4. This would be 5 pi over 4. 3 pi over 2 would be 6 pi over 4. This would be 7 pi over 4. 8 pi over 4. And then this would be what? 9 pi over 4, right? There we go, 9 pi over 4. 9 pi over 4. And then I would have 10 pi over 4. And then finally another 11 pi over 4. So it's kind of squished in there like that. Okay, so far so good. So halfway between 0 and 3 pi over 2 is 3 pi over 4. So I'll be located here. Okay. So that's then what's halfway between 2 pi and 3 pi?
10 pi over 4.
It'd be 9 pi over 4, right? Wouldn't that be the one halfway between? Oh, there we go. Okay, so they were there. I just forgot to put 5 pi over 2 on there. Okay, so what's halfway between 2 pi and 3 pi?
9 pi over 2.
There we go. Okay, so where am I at here? I am down here. Perfect. Or, yeah, sorry, 3 pi over 2 and 3 pi. And then finally I'm up here at 3 pi over 4. Wow, there we go. Totally messed this one up. But there we go. We finally got it.
So far down.
Ah, shoot, it's not. Oh my gosh.
I'm confused.
Thank you. Here we go. It's here.
It's 5 pi over 2.
Is it 5 pi?
It's 5 pi over 2.
No, it's between 3 pi over 2 and 3 pi. It's 9 pi over 4. Yeah, that's why. That's why. Okay, so this is a good opportunity for us to check, to use that point. So I'm going to go ahead and use this point. I think 9 pi over 4 comma negative 1 should be a point on this graph right here. Okay, so this is a good opportunity to actually go and check. So we're going to go to Desmos and we're going to graph that point. I'll go back in a second, but we're going to go here and graph this. So I'm going to change this. Okay, this is no longer negative, whatever. The sign is going to be over here now. We did 2x all divided by, oh shoot. Let's do this. I'll do 2/3. Ay caramba.
Wait, so it's at 5 pi over 2 or 9 pi?
9 pi over 4.
Okay. Oh gosh. That's not right either. There we go. All right, the point that we came up with was 9 pi over 4, negative 1. Here we go. 9 pi over 4, and then negative 1. Negative 1. Hey, there we go. I'm happy now. Okay, so check it out. That indeed is the point on the curve that should be at 9 pi over 4, negative 1. So let's go back. So are we okay with this? Is anybody still confused? I just forgot to put the 5 pi over 2 in there, and that messed up my scaling. So it's important to go slow, right? That's okay. All right, I want to make one more point about what does the 2/3 represent. Well, check this out, you guys. If I draw a box around 2 pi, 0 to 2 pi, you can clearly see that I have only drawn 2/3 of what the actual period is. That's what the 2/3 also represents. So my blue highlighted portion represents 2/3 of the real period, which in this case would be 3 pi. Okay, here we go. Last box here. This is going to be y equals negative 3 sine of x over 3. You can do the amplitude and reflection in one graph. Amplitude and reflection in one graph. But notice I gave you an amplitude with a reflection, and a different period, okay? So what I want you to do is graph it by hand, graph it on Desmos, and give me one point that is guaranteed to be on there, and then you're out of here.
I never know where to put the point.
Yeah, the scaling part is definitely the most part.
Like, I understand how to get to the parent graph. So then once you have